In this video, we will talk about logical and physical addresses. A logical address is an address generated by CPU while a process is running on the CPU. A logical address is seen by the process. A logical address refers to an address in the process address space. In the process address space, we have code section, data section, and the stack section. These logical addresses are the addresses in the process address space. Logical addresses doesn't exist physically, so the logical addresses are also called virtual addresses. On the other hand, the physical address. A physical address refers to a location in the main memory. We know in the main memory, every byte has a unique address. Now, the physical address is the address of this memory unit, or the address of the physical memory unit. A physical address is seen by the memory unit. A physical address is the actual address in the main memory where instruction or data is stored. The logical address and the physical addresses are the same in the compile time and the load time address bounding. The logical address and the physical addresses differ in execution time address bounding. The logical address space is a set of all logical addresses generated by a program. The physical address space is a set of all physical addresses corresponding to those logical addresses. All the physical addresses that match the logical addresses in the logical address space consist of the physical address space. In the computer system, we can have multiple processes, or the multiple processes can be loaded in the main memory. Here, the different processes can have their own logical address space. Now, the process 1 has a logical address space. Process B has a logical address space. Now, given the logical address, for example, the logical address A. Now, in the process A, at this address, it may store the instruction to initialize a variable. In the process B, at this address, it may store a data. So given the same logical address, the different process may store the different information in this address. But the physical address, every byte has a unique address, has a unique physical address. So even we have the multiple processes, they cannot share the same physical address. Now, the user program deals with the logical addresses. The user program never see the real physical addresses. Users can view the logical addresses of a process, but never see physical addresses. Now, as a user, we can print out the address of a variable, address of the function. Now, for example, we have the variable x. Now, we can print out the address of the x using $x. $% means the address of x. And we print out the address value. This is a logical address. As a user, we never can view the physical address. The logical addresses must be mapped to physical addresses. before they are used. Here we use a memory management unit. Memory management unit is a hardware device. It maps logical addresses to physical addresses at runtime. Now the CPU generates the logical address. MMU, memory management unit, translate or map this logical address into the physical address. And then the CPU can fetch the data or instruction from this physical memory address. Use this address to access the physical memory. There are many different methods to accomplish such address mapping, or the mapping the logical addresses to physical addresses. And now we will I will illustrate this mapping use a simple memory management unit scheme. And this mapping scheme is a generalization of the base register and the limit register scheme we talked about in the memory protection. And here we call it relocation register. We use a relocation register. It has the same, it's very similar to the base register we talked about in the memory protection. The relocation register holds the smallest legal physical memory space and memory address. Now for example, we have the process and its logical address space start from the 0. So from the 0 to max. This is the logical address space. The logical address space, the address from 0 to the maximum. And now this process is loaded in the memory. And now the physical address, the physical memory space start from the 40,000 to 40,000 plus max. Now this memory space are allocated to this process. The physical memory space from the 14,000 to 14,000 plus max. This memory space are allocated to this process. Now the CPU generate a logical address 346. Now the MMU will map this logical address to the physical address. Now this process is simple. In the relocation register, we store the smallest legal physical memory space as 14,000. This is the smallest physical memory address. Now the MMU will add the logical address to the relocation register. Add this two value together, get the physical address. It's a 14,346. Okay. Now this is used in the contiguous memory allocation. Okay. Now the CPU will fetch the data from this physical address. Here are two concepts we use in the memory management: dynamic loading and dynamic linking. The dynamic loading. Now so far we know that we need to load the entire program in the main memory, and this program becomes a process, and then this process can run on the CPU. But the fact is, it's not necessary for the entire program and all data of a process to be loaded in the main memory for the process to run on the CPU. Now so this is a dynamic loading. We don't load the entire program and needed data in the memory. So all the function or the routines are kept on the secondary storage on the hard disk in a relocatable format. A function or a routine is loaded in the main memory when this function or the routine is called. So the function is loaded in the main memory when it is called. Now use a dynamic loading, we can obtain the better memory space utilization because the unused functions are never loaded in the memory. So we can save the memory space to load more processes. The dynamic loading is very useful when large amount of code are needed to handle infrequently occurred cases. For example, the error handling routines or the error handling functions. If an error doesn't occur, these error handling functions will never be called. So this function will never be loaded in the memory. Operating system can help by providing libraries to implement dynamic loading. The dynamic linking. Some operating systems only support static linking. Static linking means system libraries and program codes are linked into the executable file. Now for example, we have the G++ main.o and the function.o and the -o main. Here we link all the, this is the .o. We link all the object files, the header files, and our program together to get the executable file. This is a static linking. And now the dynamic linking means linking the system libraries is delayed until the execution time. When the process is selected and dispatched to run the CPU, this process need to call the system libraries. And now at this time, the system libraries are linked to the user program. The dynamic linked libraries, or the DDL, are system libraries that are linked to the user programs when these programs are running on the CPU. The advantages of the dynamic linking is this. The two advantages. Advantage one is now each program doesn't have to include a copy of system libraries in the executable file. So now we have the smaller executable file, so we can save the memory space to load more processes. The second advantage is multiple processes share system libraries. So that means the operating system only keep one instance of system libraries in the main memory, and the multiple processes share this one instance of system libraries, and we don't need the multiple copy of system libraries. so we can see the memory space. So that's why the dynamic linked libraries are also known as the shared libraries. Okay, this is all about the logical addresses, physical addresses, and the memory management unit, dynamic linking, and dynamic loading. This video will conclude here.